which is true.
He's hoping you don't have any color or catchy tunes or whatever.
Yeah, not likely. I mean, I know this is a catchy class. All right, so general comment on the quiz. Most everybody seems to know how to do this transition from P of n to P of n plus 1. If you lost points, it was mostly from how you're structuring this as a proof. And I'll just say this one more time, and I don't really have a different way to say it. So prove P of n implies P of n plus 1. That's usually where we're going, but first you have to say what P of n is. P of n is the proposition that, and then state a declarative statement. And then P of 1 says this and show that it's true. That's your base case. And then you need to prove P of n implies P of n. So step 1, write P of n, that's the hypothesis. Step 2, write out whatever P of n says. Okay, step 3, if you write P of n plus 1, your proof no longer works. And a lot of people are still writing down P of n plus 1. Right? You cannot use that as part of your proof of P of n plus 1, because what people are doing is they're doing this, and then they're saying, therefore, P of n plus 1. Well, as soon as I write down P of n plus 1, I know P of n plus 1 is true, because I stated it was true here. But if you haven't proven step 3, you haven't proven anything. Right? And so, this example, P of n is the prop sum from I equals 1 to n of 3 to the I equals 3 to the n plus 1 minus 1 over 2. And you state P of n, and you state that. And then, typically step 3, I saw something like this. Right? And this last thing that we've written is what P of n plus 1 says, but it does not follow from P of n yet. You have to show why it follows. That's the core of the proof. Once you've shown that, then you have what you need to apply mathematical induction and show that this is true for all n. But you've got to show that this is true, knowing only this and rules of logic and algebra and all that other stuff. Right? And it's not sufficient to start from here and go down and then, come up with something like 3n equals 3n, therefore P of n plus 1. That doesn't work either. You've shown that if P of n plus 1 is true, then 3n equals 3n. You cannot conclude that because 3n equals 3n, therefore P of n plus 1 is true. Right? Your proof goes in this direction. Given this, you can conclude everything that follows. You can never take this and claim, therefore, one of these earlier things is true. And the classic kind of degenerative example is silly, but it's the same thing that I'm seeing. Prove 1 equals 2. Well, I'll say 1 equals 2, and I'll multiply both sides by 0, and I get 0 equals 0, and that's true. Therefore, 1 equals 2. Doesn't work that way. All you've shown is if 1 equals 2, then 0 equals 0. It's a perfectly good proof of that. But the converse says if 0 equals 0, then 1 equals 2, and we know the converse is not necessarily the same as the original statement. And in this case, the converse is not true, even though this implication is true. So you really gotta make sure you don't write down P of n plus 1. What you do is you write down Pn and things that follow from that. So the typical example here, add 3 to the n plus 1 to both sides. Right, and I just added the same thing to both sides of an equality. That's totally fine to write. That's absolutely true. And from here, I can apply algebra and eventually write this. right? But I'm not writing this because it's P of n plus 1 and I want it to be true. I'm writing it because it follows from this equality. And then once I've written this, then I just note that's what P of n plus 1 says, and so P of n plus 1 is true. The other thing you cannot do is say, well, P of n is the proposition here. We're assuming P of n is true. Well, let's set n equal to n plus 1 and just plug in n plus 1 in here. And so the sum to n plus 1 is 3 to the n plus 2, right? You're saying for a particular value of n, right, we're assuming P of n is true. And we're showing that then it's true for the next value of n. Okay? You also cannot start with P of n and prove P of n minus 1. That lets you induct downward and show that everything from n down to the base case is true, but it doesn't get you up to, larger and larger numbers. So the direction is important. You're trying to go from P of n to P of n plus 1. So think about that. Ask me questions if you're still not sure what the difference is, or what you did that was different from that, and we'll work on it. But the good news is, right, the actual steps for getting from P of n to P of n plus 1, it looks like everybody had those. There were a few algebra errors in the factorial one in particular. Factorials we don't get a lot of practice with. But I saw the basic steps in most people's proofs, which is good. I just want to make sure you understand what you can and can't put down in a formal proof. All right, any questions about that? So you will see an inductive question on the final exam. Probably only one, but you'll see one and it'll be worth 10 or 15 points. So.
Will we have a little study guide for class?
Yeah, I'll put something up. Don't know how useful it'll be, but I'll put something up on Canvas. And probably the last class will kind of summarize everything we've done. Did anybody think about the three-door question?
Problem?
Yeah.
Well, I'd already seen some stuff about it.
Okay.
So.
Anybody play around with it?
Depends on which odds you're looking at.
What are your best odds of winning?
At what time you look at those odds, yeah. You got a 1 in 3 chance comparing it to a 1 in 2 chance at this point.
Is it a 1 in 2 chance?
Still 1 in 3 in the end.
So remember the setup. You get 3 doors, A, B, C. You make an initial guess. Okay, I think it's in door C, and then the host will tell you it's not, and they'll tell you one of these doors that it's not behind. They'll say, okay, I'm telling you it's not behind A. Would you like to stick with your original guess, or would you like to change it? And the question is there any advantage to changing your guess at this point? Because now you've got 2 possibilities.
I don't know the answer to the question. All I know is about 20 years ago, this was kind of a controversial thing, and there was a woman named Marilyn Van Sant or something like that, who wrote a column in a paper, and there were apparently a lot of very good mathematicians who thought it was one particular way, but she kind of debunked that, and so I don't really answer the question.
It's a slippery question.
But she put out a newspaper column that it told how to solve it, and indeed convinced a lot of people, I guess, that she was right, where a lot of good mathematicians thought it was one particular way.
Yeah.
And so I don't really answer the question.
So what do you know about it?
It's better than a switch, always, right?
Why is that?
So your first choice, when you choose the first door, you have a 1 in 3 chance of getting the prize, right?
Mm-hmm.
And then when he shows you which door it isn't in, it's almost like you're selecting both of the other doors instead of just choosing one. So you have a 2 in 3 chance instead of 1 in 3.
So yeah, that's the essence of it. They tell you it's not under door B. Okay, so you can either stick with your original or you can switch. Okay, so if you guessed correctly originally and you stay with this, you're going to win. Okay? We all agree the chance of guessing originally is 1 out of 3, right? So 1 out of 3 chance that you guessed correctly originally. If you stay with your original choice, you got a 1 in 3 chance of winning. Okay, if you guessed incorrectly originally, what you want to do is switch. Well, the chance that you guessed incorrectly was 2 out of 3. So if you stay with your original guess, you're going to win 1 out of 3 times. If you switch, you're actually going to win 2 out of 3 times, because 2 out of 3 times your original guess was wrong, and switching will necessarily bring you to the correct door. So you're actually twice as likely to win if you switch your guess. But what trips people up is that when you just look at it at this point, it's like, well, there's 2 doors, it's a 50-50 chance. All right, so switching wouldn't make any difference. But in fact, you've got information from the fact that you originally picked this one. You know that's probably not the right door. And so you're better off switching. So that's just kind of a weird probability combinatorics thing. Of course, you never know if they move things around behind the doors while you're guessing.
Well, the podium spins. So.
Yeah, yeah. All right, so we're going to talk about languages and grammars. Oh, and by the way, I posted some homework on combinatorics. So some questions from the text. So that's posted today, and I'd like you to turn them in on Monday. Unfortunately, I'd rather have a day to have questions about them, but we don't have a day. But I'll be around tomorrow. So if you try these questions today, you can shoot me notes tomorrow or come by office hours if you like.
Is that a homework assignment?
Yeah, yeah.
Okay.
So that's homework 8, I believe. So that's posted, and write them up, turn them in on Monday. And then I don't know what I'm going to do for homework for this last unit. I might give you some homework on Monday depending how far we get. All right, so languages and grammars. Languages are the way that we take information and bundle it in some other form, right? That's not a formal definition. It's a working definition. And there's the question of syntax and semantics. And we're only interested in syntax. We're not talking about the meaning of a sentence, for example. We're talking about, is a sentence well formed? So everybody here played Mad Libs, right? So give me a verb, give me a noun, give me an adjective, give me another adjective, give me a noun. You plug these in and you get a syntactically correct sentence, right? But the meaning of them is usually ridiculous, which is what makes them funny. So we're only looking at syntax. And the general question is, how can we address this question of syntax of a sentence, whether it's a sentence of spoken or written text, or a sentence that's a line of a program, or a sentence that we're going to send to a web browser to request a web page. So how can we assess the syntax that belongs to a language? So we'll make all of this more formal as we go. Let me give you a simple example of a description of an English sentence. So a sentence might be a noun phrase plus a verb phrase. And a noun phrase might be an article, the, for example, plus an adjective plus a noun, or it might be just an article plus a noun. And a verb phrase might be a verb plus an adverb, or it might just be a verb. And an article is the or a. An adjective could be large or hungry. A noun could be a rabbit or a teacher. A verb could be eats or hops or talks. And an adverb could be quickly or wildly. And so there's a description of a really simple language in which we can form sentences as long as a sentence follows this structure. It's got to be a noun phrase followed by a verb phrase. And so we can create sentences like the large rabbit talks quickly. Right? And the large rabbit is a noun phrase, talks quickly is a verb phrase. This is an article, an adjective, and a noun. This is a verb, and this is an adverb. So they used to have people diagram sentences in English class. You would take a sentence and you'd break it down into, you know, this piece and that piece, and you'd break those down into other pieces. And you're basically studying the syntax of a sentence. And so this could be the hungry teacher hops wildly, and that's perfectly fine syntax. So we can take a sentence and so we can do two things with this kind of description. We can build sentences, okay, that's the Mad Lib game. We can say, okay, let's just take an article, a noun, and a verb. Right, so the teacher eats. There's a good sentence. So you can take this description of a sentence, you can break it down to, you know, either this or this for a noun phrase and either this or this for a verb phrase, any of these for an article, adjective, and so on, and construct sentences. So you can go up to a sentence, or you can take a sentence and you can analyze it and say, does it follow this structure? Right, so diagramming it, saying, well, okay, that's not a noun phrase, but that's a noun phrase, and the rest of it, yeah, that's a verb phrase, because that's a verb and an adverb, and so on. So you can do synthesis and analysis. We're interested in both.
Does this whole process depend on stating all possible articles, adjectives, nouns, verbs, and adverbs before the process even starts?
Yeah, so presumably this is the complete list of nouns that our language understands, but you know, if we could also talk about cars, we'd have to include cars as a noun and so on.
Okay, but the process that you're talking about, you have to include the list of all these things before you can continue with the process, whatever you're going to do?
Probably, but not necessarily. I mean, you can construct sentences with whatever set of nouns and verbs you have, right?
Right, but I'm just saying, well, okay, I'll stop. I got it.
Okay. Okay, so that's fairly informal. Let's formalize it. So there's going to be a bunch of definitions here, and the definitions are important. So first definition is a vocabulary. So vocabulary V is a finite, non-empty set of symbols.
That's exactly what I was talking about earlier.
Okay. Finite, non-empty set of symbols. So we would think of this more like an alphabet, perhaps. A word or a sentence over V is a finite length string of elements of V. So a word or sentence over a vocabulary is just a finite length string of elements of that vocabulary. So a string is an ordered collection of these things. It's not like a set. We could have a symbol in there more than once. Think of it like just a string from programming. We're allowed to have an empty string containing no symbols at all. We represent that with lambda. So lambda is the empty string. And it's pretty useful. And it's not exactly like the empty set, right? Because these things are not sets, right? They're strings. So a string that contains no characters, we call that lambda. All right, V with an asterisk after it is the set of all words over V. Set of all finite length strings comprised of elements of V. That's the same star you see in regular expressions, by the way, if you're in 224. And then a language over V is a subset of V star. So it's a particular collection of finite length strings of elements from V. So what I call a vocabulary you could think of as the letters A through Z. A word over V would just be a collection of letters side by side in a particular order. V star is the set of all possible collections of letters, and a language over V is a subset of those. For example, the English language is those collections of strings of letters that we consider to be words. So the terminology is not the same as what we use in commonplace. But the language would be like all the words you find in the dictionary, for example. And so we're interested in specifying languages. And there's a few ways we can do this. One approach, list all the words in the language. Do we do that? Yeah, that's what a dictionary is. That's how you know when you're playing Scrabble if something is actually a word. You look it up in the dictionary. It's a literal collection of all the possible words in the language. But that's not very good for defining the language of a C program. We could have a dictionary with every possible C program, and the compiler could simply look at your code and see if it's in the dictionary. And if it's not, it'll say, oh, there's a syntax error somewhere. But that's not practical. But for small languages like English, we can do that. Another approach, list rules for something to belong to the language. For example, at least one of your characters has to be a vowel, unless your word is syzygy. If you have a Q, it has to be followed by a U. And we can come up with rules like this, but it's a hard set of rules to come up that covers every possible word. So that's not a really practical approach. So the approach we're going to take is to use a grammar. Describe a grammar for the language. And a grammar is really a set of information that tells us how to create things that are words. going to be a set of rules that we can use to create words. And there's different types of grammars. We're going to talk about a phrase structure grammar. So a phrase structure grammar G, it's going to be a four-tuple, V, T, S, and P. V is going to be the vocabulary, so the set of symbols that we can use. T equals what we call the terminal symbols. And so T is a subset of V. S is what we call the start symbol. So S is an element of V. And P is a set of productions. Productions are basically rules for changing one word to another. But we'll make that formal presently. So phrase structure grammar is a collection of these four types of things: vocabulary, a subset of that called terminal symbols, an element of that called a start symbol, and then a set of these things that are called productions or production rules for replacing one word with another. So let's do some examples. So let's describe a grammar, VTSP. V is going to be the following set: little a, little b, big A, big B, and S. T is going to be the subset little a, little b. Our start symbol S is just going to be this symbol S. And our production is going to be the following rules. S goes to big A, big B, little a, comma, big A goes to big B, comma, big B goes to little a, little b, and big A, big B goes to B, little b.
Does the first one say S goes to capital A, capital B, little a?
That's what it says. So here's what we can do. We can start with the start symbol S. And there's a production rule which says S can be replaced with capital A, capital B, little a. And A could be replaced with capital B, which means capital A, capital B. Little a can be replaced with two capital B's for the A, and then a capital B and a little a. And capital A, capital B can capital B can be replaced by little a, little b, so each of these can be replaced by little a, little b. And now we have a string consisting only of terminal symbols. And once we have a string that we got from our start symbol using these production rules, and it consists only of terminal symbols, that's part of our language. So this is one word in our language, ABA. Now we could also have said S goes to capital A, capital B, little a. Well, we know capital A, capital B can be replaced by a little b. So from our start symbol, we could also get the string little b, little a, terminal symbols only. That's another word over our language. And if you play around with it, those are apparently the only two words in our language. So it's like half a page of description to describe a language with only two words in it. That's okay.
You can do binary off of that.
Yeah, you can.
Just takes a long time to say hi, how are you?
Yeah. Oh, you'll be surprised. All right, so that's the mechanics of this phrase structure grammar business. So let's formalize this a little. The formalization is usually not as illustrative as a couple of examples, but the formalization lets us go back and know exactly what's what, right? So we can say, well, what about this? We can go back to the formal description of it. But the formal description doesn't usually illuminate for most of us. Okay, so let W0 equal L Z0 R. And let W1 equal L Z1 R. Where these are some collections of symbols, right, from our vocabulary. Okay, if Z0 changes into Z1 is a member of our set of production rules, then we say W1 is derivable from W0. In other words, once we start with W0, if we have a rule that says Z0 can be replaced with Z1, then this new string W1 with the Z1 in the middle is derivable from W0. And we write W0 double arrow W1. And this has nothing to do with propositional logic anymore. The single arrow, the double arrow, totally different symbols. Okay, we're in a different subject area here.
So would this be like saying playing is derived from play?
Yeah, so if we had a production rule that said you can take something and add ing to the end, then playing would be derived from play. All right, if W1 is derivable from W0, and W2 is derivable from W1, and W3 is derivable from W2, and eventually some, I don't know, let's just call it Wn, then Wn is, so let me tweak this definition. W1, in this first case, W1 is actually directly derivable. It's also derivable, but it's directly derivable if it comes directly from W0. If we can follow a chain of these derivations to get Wn, then we just say Wn is derivable, but not directly so. Wn is derivable from W0. And this chain of direct derivations is called a derivation. And in this case, we write W0, double arrow Wn, but we put a little star on top of the arrow. So the single arrow says W1 is directly derivable from W0. The arrow with the star on top says the right side is derivable from the left, but possibly not directly. Okay, so here's our fantabulous definition. Given a phrase structure grammar, the language generated by V, generated by G, which we write as L of G, equals the set of all strings of terminal symbols which are derivable from S. So if G is a phrase structure grammar, the language generated by G is a set of all strings of terminal symbols that are derivable from S. So we can start with an S and we can follow these derivations and get something indirectly derivable that contains only terminal symbols. That's part of the language. And the whole language is a set of all of those strings. Knowing something about set theory, we can write this more succinctly. L of G equals the set of all words contained in T star. This is all strings comprised of terminal symbols such that W is derivable from S. So there's the nice one-line definition. All right, so you ready to play with this?
Can you have more than one starting symbol?
No, but we could get that effect by having the starting symbol go to either of two other symbols, and then we could start from either of those, basically. So I'm always going to be talking about a language G, which is a four-tuple of VT, S, and P. So I'm just going to write down VT, S, and P here. Okay, but it's the four, elements of this formal grammar. So suppose V equals S, big A, little b. Terminal symbols are little a and little b. Start symbol is S. And our production rules are as follows. So S goes to little a, big A, S goes to little b, and big A goes to two little a's. So what strings of terminals are derivable from S, given those three production rules? Play around with it and just shout them out when you find them. Yeah. Right, because we have a rule from S we can get to B. B is actually directly derivable from the start symbol.
3 lowercase a.
3 lowercase a.
Like in the end, I guess.
So
S into A, capital A, and then capital A into AA.
cool. That looks good. Any others?
Would you be able to leave it where it's the capital
got to be a string of terminal symbols, and the terminals are just the little a, little b. But yeah, that would be. Right, that's pretty much it, because from S we can either go to B and we're done, or we can go to little a, big A, and big A, the only thing we can go to is two little a's, so that's our second word. That's really it. Okay, so let's try a different one. So our vocabulary is the start symbol S, as well as a 0 and a 1. The terminal symbols are just 0 and 1. The start symbol is S. And the production rules are as follows. S goes to 1, 1, S, or S goes to 0. So what things are in this language? Definitely a 0, because we can get there straight from the start symbol. And we go to 1, 1, 0. Anything else? Give me one more. Right, so S can be 1, 1, S. And this S could be a 1, 1, S. And this S could be a 1, 1, S. And this S might be a 0. So there's an infinite number of things in this language. And they each correspond to an even number of ones followed by a 0. And remember, 0 is even, so that first thing is 0 ones followed by a 0. So this is a language consisting of all strings that are made up of an even number of ones followed by a 0. And that's an infinite set. There's an infinite number of words in this language, but our description of the language is very much finite. It fit on half a page of paper. And it's very formal. It's more formal than saying an even number of ones followed by 0. Right? It comes straight out of these production rules and the rest of the setup. All right, getting the idea of this? So let's try one more. So our vocabulary will be 0, 1, uppercase A, uppercase B, and S. Terminal symbols will be 0 and 1. Start symbol will be S. And our production rules will be S goes to 0A. S goes to 1A. A goes to 0B. B goes to 1A. And B goes to 1. And we want to see what this language looks like. And there's no fixed way to do this. It's playing around with it, basically. It's making some production trees and seeing what's in there and trying to get a feel for it. So spend a minute and play around with that. And I'll try to remember what the answer is. let me know when you start finding words in there.
So the smallest words are 0, 0, 1, and 1, 0, 1.
Right, so S can become a 0A. That A could become a 0B, and we know B can simply become a 1. Or S could become a 1A, and that A could become a 0B, and the B could be 1. So we get 0, 0, 1 and 1, 0, 1. Those are both elements of the language. Good.
I got 0, 0, 1, 1 and 0, 0, 1, 0, 1.
How did you get 0, 0, 1, 1?
S goes to 0A.
Mm-hmm.
0A goes to 0, 0B.
Okay.
And 0, 0B. I made a mistake. Did I? Yeah.
But you're really close.
Well, so B then goes to 1A.
Okay.
So then I get 0, 0, 1. And A goes to 0B.
Okay.
And then B, and then, so that's, I think I got the same one as I got.
Yeah, and then B
0,
goes
0,
to 1.
1, 0, 1.
Okay, good. So 0, 0, 1, 0, 1. And if we had started with S going to 1A instead of 0A, right, all of these would have simply been 1s. And that would have gotten us to 1, 0, 1, 0, 1.
And it keeps going because A and B can keep switching back and forth.
A and B can keep switching back and forth.
But we can guarantee that the last digit is 1.
The last digit is always 1 because that's the last terminal. Let's do this one more step. Let's find a 7 element, 7 character word. Right. So 0, 0, 1, 0, 1, 0, 1. And again, if this first derivation had gone to 1A instead of 0A, all of these would simply be 1s, and it doesn't change anything else, and so we also get this 1, 0, 1, 0, 1, 0, 1. Okay, so what's the general pattern here? If you had to describe this in words.
It either starts with 2 zeros or 1 0, and then after that it just alternates 1 0, 1 0, and then ends with a 1.
And then ends with a 1. Okay, so it either starts with 2 zeros or a 1. So a different way to say that is it starts with either a 0 or a 1, and then it's a succession of 0 1s. At least 1 0 1, but possibly more. And we could make a regular expression for that if we know regular expressions. It's like bracket 0 1 followed by 0 1 followed by 0 or more 0 1s. But don't worry about that.
I've not studied regular expressions. Where
That's
is
what I
that?
said, don't worry about that.
No, I know.
Yeah.
Where is that studied in?
That's studied in 224.
Okay.
So, and regular expressions really come out of all of this stuff, right? It's a way to describe words that we're interested in, so we can search for something by describing it as a regular expression, and it lets you do powerful search and replace. All right, so we've looked at some examples. Here's a language. Let's see what words are generated over that. That's the analysis part of language, okay? The dual to that is the synthesis part, so constructing a grammar. And here I'm going to tell you what the grammar consists of and ask you to create a phrase structure grammar that corresponds to that. So for example, let's say the language over some grammar consists of the following strings: the empty string 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, and so on. So in words, it's n zeros followed by n ones, where n is bigger than or equal to 0. So if it's no zeros followed by no ones, that's the empty string. 1 0 followed by 1 1, 2 zeros followed by 2 ones, and so on. So how could we make a phrase structure grammar that has this as its language? So any ideas? We need to define V, T, S, and P.
T is 0, 1.
Looks like the terminal symbols are just 0 and 1. Right, every string in there consists of only those characters, which means 0 and 1 will be part of the vocabulary. I'll give you S. Let's just have S be the start symbol. So we'll put S in the vocabulary also. And we need at least one production rule which says S changes into something.
The first symbol, possibly?
S could change into lambda. Perfect. That makes lambda part of our language. And then we'll need some other rules if we don't want to represent the empty string. So we'll have at least one other rule. S goes into something.
0 and 1.
S could go to 0, 1.
We can have 0 and 1 go into 0, 0, 1, 1.
So terminal symbols can't change into something else. That's the terminal part of them. I don't think I said that. But we can mimic that with some other symbols.
We can have lambda turn into 0 and 1.
If we let lambda turn into anything, that's going to be bad news. Because we can think of this string 0, 1 as 0 followed by an empty string followed by a 1. And we're going to start throwing stuff anywhere that we want.
What about like S to A and then A to 0?
Okay, let's make a new symbol A. And let's have S go to A, and then A goes to what?
0 and 1.
0,
And 1.
0, 1. So that gets us to 0, 1. We're getting closer.
A into AB.
Okay. Put a B in there.
And that can essentially. And B can go into 1.
Okay.
So that would.
We have a symbol going to itself like 0, A1.
Mm-hmm.
Okay.
Like A goes to 0, A1?
Yeah, that's what I was trying to get to actually.
Okay. So A goes to 0, A1. What's that going to do? Well, if we have an A, we can replace it with a 0, A1. And that inner A could get replaced with another 0, A1. And that inner A could get replaced by a 0, A1. That's going to give us 3 zeros, an A, and 3 1s. And maybe to get out of the infinite loop, we can let A go to lambda.
Wouldn't also, yeah, no, we can only get out of the infinite loop of A to 0, 1, right?
A to 0, 1. What if you just have these three? Does that work?
We need S to go to A.
Oh, we need S to go to A. We'll throw this one in too. So S could be empty, S could go to A, which is just a 0, lambda 1, which is 0, 1. There could be a 0, A1, which would be a 0, 0, A1, 1, and that middle A can go to lambda, so there's our double 0, double 1. Does that get us there?
We can say that S goes to lambda.
We don't even need to say S goes to lambda because S can go to A and A can go to lambda. So we could actually get rid of this one and just use these three. Or as you said, we could take A to 0, 1 and forget about A goes to lambda. And this would get us to 0, 1. This would get us to 0, 0, 1, 1. Or to 2 zeros followed by 0, 1 followed by 2 1s. So we could just have these two along with S goes to A and S goes to lambda. So that would work fine too. And it's usually not unique. There's usually different ways you can do this. And obviously we don't have to use A and B. We could use, Q and T. But even structurally there's different ways to do this. We could also do this. S goes to lambda or S goes to 0, S1. And that should get us there also. So empty string, 0, empty string 1, 2 zeros, empty string 2 1s. Make sense? So the goal here is exactly what you're doing, playing around with these things, thinking about them, trying to get a feel for how this stuff turns into, a particular language. And like I say, there's no hard and fast algorithm we follow for doing that. It's something we learn. It's like doing crossword puzzles. The more you do them, the more you sort of figure out tricks that work for you. And that's all we're trying to do is get familiarity with these things. All right, let's try a different language. So I'm going to use some symbolic notation here. I'm writing the set of all 0 to the m, 1 to the n, where m and n are bigger than or equal to 0 and they're integers. And what this means is a succession of m zeros followed by a succession of n ones. And m and n can be bigger than or equal to 0. So it's really, it's the empty string. It's a 0, it's a 1, it's a 0, 0, 1, it's a 0, 1, 1, it's a 0, 0, 1, 1. It's just 2 zeros, it's just 2 1s. It's any succession of zeros followed by any succession of 1s. including none of either or both. So this exponent notation is just a shorthand way of writing, you know, m copies of 0. So think about what kind of production rules we can make to describe this language.
You can have S go into two variables like A and B, which separately can go into A can go into zeros or A0. Can go into can also go into nothing.
Yeah,
You can have A
I'll
into
take A to lambda.
yeah, A into lambda, A into 0, or A into A0 again.
Okay, I'm going to say 0A, and I'll tell you why in a minute, instead of A0. And if A can go into 0A and A can go into lambda, these cells tell you that A could just go to 0. So we don't really need a separate one for A goes to 0. Okay, and what about B?
Same process, but B goes into lambda, or B goes into B1, or 1B.
Or 1B. Does that do us? I think that does us perfectly. That's awesome. So our start symbol gives us A and B, and we're thinking A is a bunch of zeros, B is a bunch of ones. And how do we describe a bunch of zeros, including none? Well, it could be empty, or it can be a 0 followed by a bunch of zeros. And B could be empty, or it could be a 1 followed by a B, which is a bunch of ones. And yeah, that's a perfectly good phrase structure grammar. So we'll add A and B to our vocabulary, and there you go. This is a bit of a sidebar. The reason I don't want to say something like A goes to A0 is because when we're looking at something and saying, is this part of our language? If I say A goes to 0A and I happen to have a 0, I can say, okay, that 0 in my string goes with this 0. The rest of the string should go to an A, right? And my string is getting shorter when I do that. If I say A could go to an A0, and I want to know is this part of my language? Well, S could go to an A followed by a B. Okay, could this string starting right here be an A? Well, it could be if the string starting right here is an A. And how do I know if the string starting right there is an A? Well, I say, well, it could be an A starting with an A, right? And if you try to code this up, when we actually write code to do this parsing, which we're not going to do, when we actually write code to do this parsing, it's going to, you know, is it an A function? The first thing it's going to do is say, is it starting with an A? Right? And that's going to call this function and say, I don't know, let's see if it's starting with an A. And it's going to call, is it starting with an A? And you're going to recurse forever, and you're never going to come out of it. If you write it like this, is it an A function is going to say, does it start with a 0? Yes. Okay, let's see if the rest of the string after that first character is an A. It's going to call, is it an A, with a shorter string. And after you do that n times where your string had n characters, you're going to come down to where you're calling an empty string, and you'll either say, yeah, A could be an empty string, or it can't. So that's a detail for a later course. But the spirit's the same whether you do 0A or A0. Good.
comfortable enough going from G to LG,
Mm-hmm.
but going from LG to G,
Yeah.
a little more,
Yeah, that's the synthesis part. Synthesis is usually harder.
like you said, there's no hard and fast rules, and just kind of,
Yeah. Well,
Yes,
let's
I'm checking.
let's do some more of those.
it's not as easy for me.
I don't think it's as easy. Well, there's probably 10% of the population that it's easier for. I'm not going to keep saying that this is an integer. We'll just assume it's an integer. So let's look at a language consisting of 2 or more 1s followed by a 0. So 2 or more 1s followed by a 0.
You could just say S maps to 1A 0, and A maps to either 1A or 1.
So S is 1 followed by an A followed by a 0. A is either a 1 or it's a 1 followed by an A. I like that. So logically, what does A represent? It represents 1 or more 1s, right? It's either a single 1 or it's a 1 followed by 1 or more 1s. So it's any string of consecutive 1s having at least 1. And so S is a 1 followed by 1 or more 1s followed by a 0. That gives you that language. Beautiful. Let's do one more. So here I've got 3 zeros in parentheses raised to the n. So this is either 3 zeros, 6 zeros, 9 zeros, and so on. Is there anybody else?
S can go to 0, 0, 0, or 0, 0, 0, S.
That looks good to me. So our start symbol can go to 0, 0, 0, that's our first word. Or it can go to 3 zeros followed by an S. And if that second S is 3 zeros, it gives us this. So S is some collection of multiple of 3 zeros.
So you can reintroduce the start symbol.
Yeah, the start symbol is just a plain old symbol. All right, so that's phrase structure grammar. And like I say, the more you play with it, the more it starts to click. But it's certainly a bit of an unusual way to describe things. But that's what we're all about this week and next. All right, we got 5 minutes left. Let me start. Bacchus-Nauer form. This is usually just called BNF. So here's Backus-Nauer form's description of the C programming language. And it's not that long. There's some stuff down here, but as a BNF, it's actually fairly small. So we have some things like letters, which are A through Z, digits, which are 0 through 9, and ID, which is a letter followed by a letter or a digit or an underscore, any number of those, and so on. The general structure of a BNF is we have a symbol and then a colon. I don't like this BNF. Let me do a different one. This is a more typical one. So we have a symbol like a storage class specifier. Colon equals says this symbol is either an auto or a register or a static or an extern or a type def. The pipe is an or, just like in C. A type specifier is void or char or short or int or long or float, etc. And these things get nested. So a constant expression is just a conditional expression. A conditional expression is a logical or expression, or a logical or expression followed by a question mark, followed by an expression, followed by a conditional expression. And a logical or expression is a logical and expression, or a logical or expression followed by a double pipe, followed by a logical and expression. Right? This gets very recursive pretty quickly. But it's a different way to describe things that belong to this language that we call C, right? And so sometimes these things come down to terminal symbols, right? An expression is an assignment expression or an expression, comma, assignment expression. An assignment expression is conditional expression or a unary expression or an assignment followed by an assignment operator, followed by assignment expression. And an assignment operator is an equal sign, a star equal, a slash equal, a plus equal, and so on and so forth. And unary operator is, an and, a multiply, a plus, and so on. And so you can break these things down into actual symbols, and you can take a line of C code and you can tell whether or not it's one of these things. And this is the kind of specification that's used inside a compiler. Right? So you code this up and you have some software that ingests this, and it can basically take a line of C code and it can say, is this syntactically correct or not? And you can put that together and you can take an entire C program and say, is it syntactically correct or not? And if you get down to a point where you're supposed to have, a specifier qualifier plus an abstract declarator, and this is not an abstract declarator, then you print out that line of code, and right after the plus sign you say expecting abstract declarator, or maybe something more meaningful. And that points you pretty close to where your syntax error is. And BNF was another one of these big hammers I discovered when I was first programming. I found a package that lets you take a BNF and process it using assembly language, and I ported it to C, and then I just started using parsing for everything I needed to do that I couldn't use an associative array for. I will just show you. That's a little more than difficult to read. This is a binary Backus-Nauer form that I wrote out for an expression, just a plain old sort of generic expression. An assignment statement is a variable followed by an equal sign followed by an expression. An expression is an expression, operator expression, or parenthesis expression, close paren, or a variable or a number. And a variable is a letter followed by a var2, or it's just a letter. A var2 is a symbol followed by var2 or a symbol. Symbols are letters or digits or underscores. And so this will successfully match things like parenthesis a plus b times c. but will tell you that there's a syntax error if you try to do something like paren a plus b times c without a matching closed paren. Because this paren, when it saw the paren, it said, okay, all of this has to be an expression, and then there needs to be a parenthesis on the end. And this will match as an expression, but it will miss that last closing parenthesis. So BNF doesn't get talked about a lot in modern courses, but it's a pretty powerful way to describe syntax. All right, so we're going to go away for 7 days and eat too much food and forget all of this. But when we come back Monday, I'm going to talk about finite state machines, okay, which if you've done 250, you know about. We're not going to make big state tables, and we're not going to do flip-flops. We're going to talk about them from kind of a programming perspective. And finite state machines are going to take us into language recognition, and they're going to take us into Turing machines. And a Turing machine is kind of a theoretical finite state machine. It's the one that, you know, our modern computers are based on. And from Turing machines, we'll talk about non-deterministic Turing machines, which are Turing machines with genies inside. And that'll let us talk about classes of problems and difficulty of solving problems, which will take us to questions of computability and how to win millions of dollars in computer science. So we'll do all of that next week, Monday, Wednesday, and then Friday we'll probably just kind of summarize what we've done so far. So have a good break if I don't see you in class tomorrow, and I'll see you next week.